Okay, we are now recording the session.
Thank you all for joining us for this 2021 Student Symposium Continuing Education Seminar titled MLS in Austin, Design of Q2 Stadium. Before we get started, please let me share a few technical instructions with you. If you're having any technical problems, please visit Zoom support at support.zoom.us or type your question in the chat box. The recording of this seminar without permission from ASCE Texas section is prohibited. All participants are muted throughout the duration of the seminar. If you have questions, please type them into the chat box in your control panel. Questions will be addressed at the end of the seminar. Now, a quick message from 2021 Student Symposium champion, Walter P. Moore.
Engineering.
Now, I am pleased to introduce our presenter, Mark Waggoner, a principal in the Austin office of Walter P. Moore. Mark is a leader in the field of long-span roof design and has contributed to the design of more than a dozen long-span roofs for sports facilities, including AT&T Stadium, SoFi Stadium in Los Angeles, and the under construction UT Basketball Moody Center. Mark has special expertise in the development of innovative structural systems, including kinetic structures and alternative materials, as well as delivery of digital design models for downstream manufacturing use. He frequently works with contractors to develop erection plans and design connections for complex structures in collaboration with Walter P. Moore's construction engineering practice. In addition to project work, Mark is active in a variety of national technical committees, including the ASCE SEI Disproportionate Collapse Standards Committee and the Tensioned Membrane Structures Standard Committee. He earned his Master of Science in Structural Engineering from the University of Texas at Austin and graduated magna cum laude from Washington University with a Bachelor of Science in Civil Engineering. Mark is a licensed professional engineer in Texas, California, and Manitoba. Mark, thank you so much for joining us. As you know, your alma mater, UT Austin, is the ASCE student chapter host of this student symposium, and they are proud to have you here today. Please begin your presentation once you're ready.
Thank you, Heather. Thanks for having me here today. Everyone can hear me okay? Or Heather, just tell me you can hear me okay?
I can hear you fine, thank you.
All right, and you can see my screen, I hope.
Yes, we can.
All right, thanks again for having me. That was a fun little video there. I don't think I've seen that one before. Those were like real people that work at our company. That was great. Going to talk today about Q2 Stadium, which is the new home of the Austin FC MLS franchise, which is with MLS play starting up. I'll talk about that in a minute, but this is a project we've been working on for a few years now, and it's just about ready to go. Little background on the project. Back in October 2017, the MLS franchise in Columbus, the Columbus Crew, announced a move to Austin. Following that, in August, the Austin FC brand was first announced, and then there was like a little swap. The Crew actually got sold to a new ownership group that allowed that franchise to stay in Columbus. And then the Austin FC franchise became an expansion team that starts this year. So it's kind of a win-win for everyone on that. Stadium broke ground at the time. It was called McCalla Place Stadium in September 2019, and really fast construction schedule. In August 2020, we completed the main part of the stadium structure and then sat around and watched the grass grow. Our schedule was driven by finishing in time to get all the cranes and the equipment off of the field so the pitch could grow and be ready for the season. So the first home opener at Q2 Stadium is going to be on Saturday, June 19th. The club plays away for the first few games, and then we start at Q2 Stadium in June. In fact, this is kind of an auspicious day. Today is the first match for Austin FC. It's at 5 o'clock Central this afternoon. Everyone tune in on Fox, playing at the LAFC club in Los Angeles on the campus of USC. In fact, we'll see that stadium in just a moment here. So for those of you, UT students who are on, who know Austin, I was born here, grew up in Austin. And when we started talking about the stadium, everyone kept talking about McCalla Place, and I'd never heard of that. Turns out it's this shaded piece of land right here next to Breaker and Burnett Road. And for those of you who are familiar with the Pickle Research Campus up there in North Austin, it's directly across Burnett Road from that, and the little longhorn there is on the world famous Ferguson Structures lab, where I know a lot of folks in our firm worked as grad students. So kind of north part of Austin. If you're familiar with the Domain, it's kind of catty corner across the intersection there. There's a little tire shop on the corner where I got new tires a few years ago. So it's a kind of a strange place for a stadium, but an up and coming part of Austin here to develop. So a little bit about the project team. Our client was Gensler. They were the architects for the project, both out of their Los Angeles office and their Austin office. We'll talk about why that is in just a minute. CA Icon was the owner's representative. Ourselves, along with Ruben Martinez and the good folks over at Martinez Engineering, were the structural engineers. CBD and Garza were civil engineers, and then you've got all the non-civil engineers. I will say, for the students out there, get used to working with other engineers. I would say, even though clients are mostly architects for us, I spend probably more than 50% of my time working with other engineers. So kind of learning how to work with each other starting from school is a great trait and very valuable trait. So, okay, a little bit about MLS stadiums in general. We work on a lot of stadiums, everything up to MLB and NFL stadiums. MLS is a little different. Obviously, it's kind of an up and coming league, and tend to be about in the 20 to 30,000 seat range, depending on the market. But they tend to also be very austere buildings. The economics of these clubs is a lot different than a major league club or an NFL club that's got big TV contracts. So the budgets for these projects tend to be in the range of 100 to 350 million. Q2 Stadium is around 250. Won't say the exact number, but it's in that range. Whereas MLB, we just did Globe Life Field for the Rangers. That was about $1 billion, and NFL all the way up SoFi Stadium is north of $3 billion. So it's a little bit different mindset when you're designing for an MLS stadium. And I'll give you a few examples. This is one of our first MLS stadiums, BBVA Compass Stadium in Houston for the Dynamo in 2012. It's about 22,000 seats. This is very austere. It's a little nicer than a Texas high school football stadium, but not that much. It's got some canopies to it, little bit of premium content for suites, but not a lot of that. But there's a very fervent fan base around MLS. These are some of the Dynamo fans. So the Austin FC supporters groups are going to have to match this kind of energy. Another project, this is up in Toronto. This is BMO Field. This was an existing stadium that was expanded to house the MLS club up there. We actually worked on this one for the steel contractor and doing erection engineering for the roof here. So we worked out all the crane lifts and shoring and those kinds of things to erect this roof. So they put a new covering on it and expanded the seats to accommodate this existing stadium. Orlando City Soccer Stadium, I guess it's called Exploria Stadium now, opened in 2017, about 25,000 seats. Got a pretty decent canopy to it, but the seating is pretty straightforward, not a lot of suites or anything like that. And with Allianz Field in St. Paul, so this is for the Minnesota United Football Club, opened in 2019, about 20,000 seats. And you start to see a little more high design come into this one. This actually has a tensile membrane skin that we helped develop the material for, that you kind of see it glowing there, wrapping the building. Shot during the daytime. These are starting to look a little bit more now like a smaller version of an NFL stadium, and they certainly spent more money on this than the prior ones that we showed you. Just a little bit on the section here. And you can see the material that wraps the skin there. It's a laminated PTFE mesh. So a little more high design element coming into it now. And then this is where the Austin FC debut match later this afternoon is going to happen. This is Bank of California Stadium in Los Angeles. It's on the campus at USC. You can see downtown LA there in the background. Our office in LA is that building right there in the middle. And this was going on at the same time we were working on SoFi Stadium, kind of down the street towards LAX from this. But again, it's a little more developed now. This has an ETFE skin around it, a fairly large ETFE roof, pretty substantial canopy. We're starting to look more and more like maybe European soccer stadiums in the design. And more importantly, the sports architect team over at Gensler in the LA were responsible for this design, and a lot of those same folks came and worked on the Austin FC Stadium with us. So there were a lot of reference points to Bank of California Stadium. It's about 22,000 seats. And then this is actually a future one that we're working on now. Really popular in Nashville. So it's a bigger stadium, about 30,000 seats in Nashville, fully covered roof. Nice open air kind of concourses. Here you see what it'll look like from the inside. This is under construction now. So just a little bit there about MLS in general and kind of how that market looks. And so I'll get into Q2 Stadium more specifically now. This is an overlay on a soccer pitch here of different canopy coverages for some of the projects I just showed you. This was a huge deal for ownership here. We know in Austin, especially during the MLS season, you're playing during some of the hot months. And the fan comfort was a big driver in the design of Q2 Stadium and led us to a very large canopy, a canopy that is the largest in MLS. And that's obviously to get shade for the fans. You see the Austin FC canopy outline there in green that we came up with. The next biggest one is the one I showed you at Toronto FC at BMO Field. That's the red outline. And then they kind of get a little smaller from there. Minnesota United had pretty good coverage, but there's still about 50,000 square feet more in the Q2 Stadium roof. So, and really that idea about the fan experience came from what we know about the experience up in Dallas with FC Dallas. They've got some covered seats, but by all reports, and maybe some of you have been to MLS matches up there, but it's a pretty hot, sweltering experience to sit outside, especially for a day game up at FC Dallas. And that was something our owner was very aware of and wanted to make sure that the design of Q2 Stadium considered fan comfort as kind of the paramount consideration in coming up with the roof coverage. So you see FC Dallas, pretty exposed condition. So this is this is actually an early slide in design. We changed a few things about this design, but from a coverage standpoint, this is more or less what we ended up with. About 200,000 square feet of planned coverage. You see the area there in purple is referred to as non-watertight. That actually just, it doesn't have a roofing surface on it. The metal roofing is the roof surface. So the project saves a little money that way. Really heavy rain, it might drip a little bit, but this is primarily intended to be a shade cover canopy. And then at the two ends where the blue is, down on kind of where the roof wraps around on the north and south ends, you see there's fully waterproof roof with a roof membrane and everything for a little more coverage over there, but primarily a shade canopy roof and a very large one as part of the distinctive design here for Q2 Stadium. Just some shade studies, few different, the top and bottom are options, but kind of look across the top line here. So this is July 1st at 1 o'clock in the afternoon. Two sides are fully in shade, the field's fully sunny. By the time we get to 4 o'clock, this is the west side over here on the left, so it's sort of self-shading itself. A lot of the premium content is over there, so that drove decisions to put a lot of the premium stuff over on the west. Obviously with the sun angle, you're getting a little bit on the lower seats here on the east side. My brother-in-law seats are way up here in the middle on the top, so he'll be mad at me if he doesn't get shaded nicely. So and then by 7 o'clock, we've got the field in full shade, little spotty shade coming through openings, but still quite a bit of coverage on this roof from a shade standpoint. All right, so with the background of the stadium in mind, this is an overview of the seating itself. Again, this is designed to be a very sort of economical, efficient stadium. You don't see the stands wrapping all the way around like it would maybe in an NFL stadium. We've got really 4 distinctive stands on the 4 sides of the stadium. So I'll start over here on the east stand. And the east stand is very straightforward. It's just purely seating. There's some concourse amenities out here in the back, just in low-rise, very simple buildings, restrooms and concessions and things like that. But the experience over there would be very much like going to a high school football game or something like that. It's just seating over there. As we wrap around to the south, I'll show you more about this in a minute, but there's a big opening here where temporary seats go, and that's to accommodate a stage. There's a scoreboard over here on the south, and there's an elevated concourse and some program space in terms of support structure underneath here that I'll show you in some details coming up. But really the south stand represents kind of scoreboard and stage when the building's used for concerts. The west side is where we put all the complex stuff, all the suites, all of the premium content goes over on the west side. There's a club over there. That's where the higher dollar seats are. That's where the if you buy club access, that's where you are over on that side. So all the complexity really went into the west stand. And then on the north stand, there's really only seats in the lower bowl on grade. And there's what started out as an administration building and turned into a little bit of a team store as well as a beer hall over there at the north end, but housed in just a really conventional, very economical concrete building over on that side. So here's the site. As we started out construction and got through excavation, we're a really favorable site from a geotechnical standpoint. Not too much clay or anything like that on this site, and the Austin chalk, really firm limestone bearing layer was, depending on where you are on the site, between 10 and 15 feet down. You see us here excavated down to the field level, and it's about 20 feet down from the surrounding grade to the field. You can see that they've sloped the excavation here, and we're just going to put seats on grade over there on that east side. And in various other parts, that's an extremely economical way to build. And then you see it kind of laid back for some of the elevated structure and retention back there. But pretty simple site to excavate. Usually in stadiums, we want to enter the stadium on the main concourse. That should equate to grade. That way you can walk out and either go down to your seat if you're down low, or go up to your seat if you're up high. Just a quick tour around the different seating sections. So this is down at the north end. So we've got that sort of simple concrete building that houses the beer hall and the administration offices here. You see a canopy, which I'll get to in a minute, and just seating on grade. It really couldn't get any simpler than this. Here is that building under construction. These are panform beams and a concrete moment frame system, just like you would build, say, an office building in Austin. It's pretty straightforward. And here it is completed, looking over at that north end. So you see that building with the cladding on now, the canopy above. Now there is a provision. This was designed for future seats to fill in the space sort of above the lower bowl seating. So we can add seats here in the future. And in fact, I think we're already starting to make some moves towards adding those seats back in, given how popular the sales of the tickets have been. All right, moving our way around, now we're down at the south end. So this is where we house the scoreboard. There is an elevated level of concrete here. The lower bowl seating is no longer on grade. There's some steel rakers that drop in there, kind of at the last thing that goes in, and then a steel structure supporting the scoreboard up here. And out back here, we've got some restrooms and concessions. And so looking across at it, you see the scoreboard framing coming in here, and you see a big opening in the middle. Again, this is pretty simple construction. And then here you see it mostly done. They're working on the scoreboard in this shot. Now you notice this big opening here in the middle. That's intended to be able to put a stage there, and you'll see up in the roof above that we've got sort of a thing hanging down from the roof here. This is a rigging grid, so that the show can come in and hang the lights and speakers and whatnot from this canopy roof above. So we had to accommodate about 150,000 pounds of rigging load above the stage here. So as if Austin needed another concert venue, we've got one now up here in North Austin for a certain size show. But so when there's not a stage here, there's sections of temporary seats that fill in that opening. These are grow lights here, by the way. I was taking this picture one evening when they were trying to get the grass to first start growing. All right, moving over to the east side. Again, very simple section, steel framed upper concourse, precast seating. You see the roof up above, which I'll talk about in a minute, but lower bowl's on grade, and we've got these buildings out here, the concession buildings that sort of make it nice and simple. Pretty straightforward shot during construction, looking down the east side, and here it is all complete. So nice green seats, or verde seats. And on the west side, this is where all the complexity is in the seating bowl. There's two typical sections. Part of it's on grade and lower bowl on grade, and some premium content and club space up here. As we go further down, we actually go below grade, so we have a retention system we have to deal with, holding back the excavation on by the frame, and same upper bowl and club spaces there. And this is just a diagram of what we have to do to resist soil loads. We're engaging some of the concrete frame back behind there to resist those loads. So there's very high loads going through the lower seating section because it's sunk down below grade. And the section during construction, see the steel frame going up, getting the columns ready for the roof. And then completed section, still working on a few things, but more or less structurally complete. Upper bowl, here you've got suites, and then there's the club space kind of back behind that. All right, I'll get into the roof design now. We do a lot of roofs for big stadiums. This one was kind of a nice in-between size for us. We could try out a few different things. Basic structural system here sits on 4 big concrete columns. These are 5 foot square all the way up, and we've got a span of 430 feet in the long direction and 312 in the short direction to fill in the roof. And this gives you a sense of the system. So this is one of those big concrete columns in the corners we saw there. And then spanning between those concrete columns, spanning the long direction, we've got a 32-foot deep primary truss. And this is made up of W14 sections turned sort of horizontal, which makes them nice and easy to connect. And then spanning from that truss over to the back of the bowl, and we have columns coming up on every grid line at the back of the bowl. We've got a W36 girder that does that. That's about a 75-foot span that it's got to deal with, and it's nice light roof loads. We can make that work all day long. That girder is braced by some W18 purlins that are what we would call torsionally connected, torsionally bracing the big roof girders there. So, and then coming out towards the field, we've got an extension of those roof girders that's propped up with some braces. And this sort of further shades the field and kind of balances the section on the big truss, gives us better coverage. And then on the next slide, I'll talk about this corner, which is kind of complicated. This is a shot from our model looking back at that corner. There's actually no support out at the far end of the corner. It sort of floats there and hangs, but we've got HSS columns on the extension of the primary truss. So this primary truss kind of comes through the main columns, goes out to this outrigger column here. Same thing in the other direction. We have an outrigger column here and a column here. And so this is actually sort of a series of full depth two-way trusses. So this starts out at the same 32-foot depth out here, tapers down to shallow depth at the perimeter. And these kind of cantilever out this way, but they also cantilever out this way to float that corner. And we just put a temporary shore in that corner as we were erecting it to hold it up. And then when it's all done, we take that shore out, or actually it lifts off of it. I'll show you that in a little bit. A little bit about the roof lateral system. If our concrete columns were doing all of the work, say for wind loads, they would be purely cantilevered out of the ground. They'd have to be a lot bigger than that 5 foot by 5 foot. But what we're doing is basically making a moment frame with these outrigger columns below. So this is a big kind of, think of it like a big portal frame, but the big overturning moments get distributed as couples out here at the end and to the concrete column. So the column, effectively that bending arm between those two forces is doing the work instead of that concrete column section having to do all the work. And it just has to take the shear between here and here and kind of some localized bending, so we can keep it fairly slender for the size that we are here. And same thing happens in the east-west direction. Effectively with this east-west section, we get some moment continuity that way, and we've got this outrigger effect, can keep things nice and stiff. And then we supplement that by every every column line along the back of the bowl is a kind of chunky, it's really a vertical beam, not so much a column, but cantilevering up and bracing the roof horizontally at each grid along the back of the bowl. So that's what's happening along the sidelines. Just a few connections. A lot of times now we're fully modeling all these connections in Tekla as we do the design. So this shows the way that the main trusses sit on top of the big 5-foot concrete columns with the rebar, making sure the anchor rods aren't hitting any rebar. That this is all constructible. This went pretty smooth for us. And this is where those big trusses, the bottom cord of those big trusses cross the column. We spent a lot of time going back and forth with the contractor on this. They actually built a mock-up of this thing, but it's not too hard. There's compression, pretty large compression going through the column, but no tension. So we've got some bearing plates that bear on the face of the column. We just need to provide quite a bit of adjustment to account for the concrete tolerances in a situation like this. All right, so here you see this is the east side and the roof all done here. And you can kind of think of both the east and west sides as an extruded section that goes all the way down the east and west sides with this curve over sort of to this point and propped back up to that roof edge. They're identical and symmetric to each other, east and west side, as far as the roof is concerned. And then we have to fill in between that for the north and south roofs. And we went back and forth with a lot of different schemes for the north and south roofs, but we ended up with something that functions very much like a stay cable bridge. So we've got our sort of extruded section over. I'm now looking the other way. This is east, this is west. And then from the top edge, we're dropping cables to pick up this roof platform down low, almost like it were a bridge, right? So we just cantilever out essentially from each side and then meet in the middle of this central section. And literally that's how we built it. I'll show you on the next slide. This is sort of a force diagram. So we got our downward load here in the middle of the roof. These stay cables going down to these points are picking up the downward load, which is great. But we've still got wind uplift. So if that were the only system, then we'll get wind uplift, which a lot of times in these roofs exceeds the weight of the roof. It would just flutter upwards uncontrolled. So we have to have a way to hold it down for wind uplift. So you'll see there's a bowstring cable that we've added. It's kind of superimposed on the system that provides the uplift resistance working with the downward cables. It also gives us a way to kind of pre-stress the system against each other. The other nice thing with this downward load, you can see we kind of balance the section on these super columns over here. And actually what happens is this corner, this freestanding corner that I showed you, actually lifts up a little bit because we're balancing it with the weight in the middle here. We can keep this edge floating in a really nice way just by letting gravity work for us on this little teeter-totter here. All right, so I mentioned that we literally built it like a bridge. So first thing that happened, we pre-assembled these panels on the ground, and they're about 40 feet square. Lifted them up with a crane. The crane would hold it there while they hook up the cable. They held the side that the cable goes on just a little bit high, so you could pin the cable with the cable slack, let the load off the crane, and the weight of the panel itself tensions the cable, which worked really nicely. That's the first panel. Here you see the next panel having been lifted up, and they're fitting it onto the first one, a fairly complicated pick here, but holding it in a certain position while they attach the cables, the permanent cables, so they can let it go from the crane. So you do that from both sides. We're kind of cantilevered out to our third cable left and right, and on a day and the temperature was some magic temperature that this fit perfectly. They could just drop the center section in, connect it up, and we were done. All right, so after those downward cables were in place, they came in, strung this uplift cable that you see going across here. It sits on some struts that extend up to clamps. And then we had to tension these cables with some hydraulics to get the right pretension in the uplift cables. All of these cables are what's called full locked coil cables. It's got these Z-shaped outer wires protected with a nice Galfan coating. And so every cable here is the same size. They're all 60 millimeters in diameter, have about an 800 kip breaking load to them. This is the factory where the cables are made in Germany, in Memmingen. Just not too far outside Munich. We were there actually for another project, but these are some shots of some big cables laid out on their floor. And way down there at the end, they have what they call the speltering tower, where they put the sockets on the ends of the cables by pouring molten zinc into them. It's made by a company called Pfeiffer. These guys have been making ropes of different kinds for about 400 years now. So they supply a lot of cables on projects that we work on. A little better shot of maybe the cable system here. So you see the 3-stay cables coming down. We've got adjustable sockets on the bottom end, so we can adjust for any tolerance in the steel. And then you've got the uplift cable system here. You see it kind of offset. We couldn't have that uplift cable in the same location. It would just hit the other cable. So we put it halfway in between on these V-shaped struts that come up and support the cable. So it comes along, and then at the end it splays out with 2 cables to resolve the load back as kind of a compression in this girder running east-west. So that's how the uplift cable system works. Shot here up on top of the roof of those cables installed on top of those V-struts and the clamps. Some close-ups of the sockets. This is one of the adjustable sockets. The way this works is there's a cross-threaded piece of rod here that can spin to adjust these 2 pieces back and forth relative to each other. These are fixed sockets up at the top where it connects in. These are all sort of zinc coated for corrosion protection. This is a clamp body out on top of one of the struts. So you basically just kind of make a groove in some plates and pre-tension some bolts together to get enough clamping force so it doesn't slide on the cable. This is the weldment where the V struts come together, and these are the bottom cables anchored over near the roof. We have to penetrate the waterproofing and make sure this doesn't leak around the lug plates coming up. Okay, just a little bit about the people involved in the construction. The construction manager here was Austin Commercial. Those guys did a great job building this thing in a really short amount of time. Most of our work on the steel side was with Irwin Steel out of the Dallas area, and then Bosworth Steel Erectors, who we do quite a bit of work with. And then on kind of the consultant side, we company called MXC Consulting, which is our construction engineering sort of arm of our company, worked for the contractor doing various modeling and erection engineering tasks. And there's a company called DBM Vercon BDS, who were the steel detailers, and the east and west roofs, the erection engineering was done by Stan Lindsay, working for Bosworth. So. And then we did the erection engineering on the cable pieces. Just a little bit about how the east and west roofs were built. There were 2 shore towers that Bosworth owned. So you see them here over on the east side. Those are put up, and then the truss sections that run between them, and it's about, I don't know, a little over 100 feet in between these shore towers. This section was all assembled on the ground, lifted up by a crane, set on the shore tower, braced by these W36 girders to hold it there. And then once the roof was done, in fact, this was taken on the day we were deshoring the east side. You come in here, and there's a header, and there's some hydraulics up here. You able to lower this header to take the load off the shore tower and let the truss span. So it's always a big day when you deshore one of these trusses, and you can see that it's working like it should, it deflected like you expect it to, and all those kinds of things. This is our computer analysis model for the project. This is in the SAP 2000 software. So we spend a lot of time with these models. This one has quite a few stage construction features where we actually build the structure step by step, the way it was built in real life, because there's some, there's sequence effects that get locked into these roofs that are pretty important. There's a bunch of wind loads in here, and so this is what we use to really drive a lot of our design process. We did do a wind tunnel test on this project. This was tested in the wind tunnel up at RWDI in Guelph, Ontario, Canada. We work with those guys on a lot of our projects. You can see some of the surroundings here, and then they've got some things that get the turbulence right. And you can't really see it here, but there's probably 1,000 little pressure taps on the surface of this model that they read the wind loads on, and then do some processing on that and give us loads to use in our design. This is the wind climate in Austin, and plotting recurrence interval versus wind speed. And this is actually the code number. You can see where the real numbers are a little bit less than that, but we tend to kind of scale things back up to the code number. And then these are just different directionality of the winds in Austin. A little bit on the construction. This was probably one of the fastest projects that we have ever designed. And to make that possible, one of the things we did, as this is supplemental to our normal services, but we built a fabrication model, sometimes called a level detail 400 or LOD 400 model, in the Tekla platform. Basically, this model has every last bolt and weld and cut, and the steel is exactly like it will be fabricated in the model. And then we're able to hand that off to the fabricator. They just extract the shop drawings and can go straight into fabrication, basically. So the schedule here was so fast that we were working on this model before a fabricator was selected. Once they were selected, we had about 2 weeks to give them the first sequences in the model. That way they could extract and get to fabrication almost immediately. And that's a process that usually takes several months from finish of design to start a fabrication. So there's a lot of things we're doing in the steel market these days to make these projects go extremely fast. And you can see here, we also use the same model for a lot of crane planning on the erection side. We've got models of the cranes in here showing how each different pick is going to be done for the roof erection. So here it is, almost all done. And just putting the last bit of roofing on. Someone took a drone up and took this picture, so you see it from above there. And this was a little bit later, taken from the inside, just kind of working on the field and the last few seats. But this is pretty well how the interior fan experience will be in the stadium. Turned out pretty nice, I think. So with that, I'll kind of wrap up. I think we got a little time for questions. This is how we had to do our site visits. So the pandemic was pretty strange from that standpoint, but a lot of distant in-person site visits and a lot of virtual site visits and things like that. But the construction team did a great job of getting this thing done. And as a final reminder, don't forget to watch the debut game today. So that I'll stop. If we have time for questions, happy to take any.
Yes, we do have a couple questions here. Thank you. So in the chat here, there's a question. What was your favorite part of designing, building this stadium? And do you have an exciting, innovative method you used in the designing or building?
Okay, favorite part? Oh, I don't know. It's always exciting. I think I had the slide up there, deshoring. Usually we like to go out there and be there while they deshore. Fortunately, never had anything go wrong, but it's always an exciting time. If you think your professors have probably, run the old Code of Hammurabi past you, where the builder has to go stand under the thing, right? So we're always nearby when they first take the shores out to make sure it goes well and we're a part of it. So and then the second part, something, I don't know, we try to be innovative in the design. Really it's just a process of working through what's right for each project. So
yeah, and Sean, kind of to add to that, comment earlier about the shoring. Are there any scary stories you have from past projects when removing the roof shoring?
No, usually it's pretty planned out and goes pretty well. We try to avoid the scary in these things. We do every once in a while, we'll find, we put these shores in, and when the roof is done, you've got something you can push against. And so if it gets really hot, the shores actually expand in their length, and you can get a little extra load in there if it's a hot day, and you got to make sure that you got enough hydraulics to get it under there and take the load off. But no, we try for it not to be scary. So.
Good. Another question. During the recent winter storm, did any problems come up or any concerns?
We didn't have any problems. We were talking to the facility, kind of making sure all the drains were clear and things like that. But I was keeping an eye on it on the webcam. I guess the power stayed up to the webcam. I could kind of watch it, but no, it's fine. I think with the amount of snow we got, we were within the load that we designed the roof for. But it's definitely a test for the roof when you get something like that. So.
Great. Another question. Are there any new design methods or strategies that you developed through this project that you will continue to implement in further projects?
Well, I think the cable stuff was fairly new for roofs like this. It's been done in bridge projects, but and it's been done. There's specialty cable firms, and Pfeiffer's one of them. They don't just make cables, but they build cable structures too. But we built this one just with the folks at Bosworth, kind of regular steel erectors, and I'd like to think we made it simple enough that that kind of construction method is maybe a little more accessible to more people.
Okay, and we've got room for one last question, and I'll bring this one up. The balancing of the moments on either side of the column to generate an uplift at the end of the frame, is that something that's done often?
So in bridges, there's something called balanced cantilever construction, where you erect, say, a segment of bridge either side in a stay cabled arrangement to keep it balanced as you work your way out from each tower. And what we did here is very, very similar to that, and just a matter of kind of going back to first principles and making sure that you're not things balance nicely, and you can find yourself getting lost in the computer programs and things like that. But if you sit down with some quick, really simple free body diagrams, you can work out that you can create a favorable balance situation like that with a few simple tweaks to the design. So.
Okay, thanks for the response. Now, everyone, we'd like to keep your attention just for a few more minutes to share the special message from ASCE about their future world vision.
If you don't make a plan or make a goal and have a vision, then you just react your way into the future. And that's not what we want to do as civil engineers. We want to lead into the future.
How we do our jobs as civil engineers, maybe as systems engineers, will be different in the future.
What are the different cities we see evolving, and how can we really get an understanding of those cities? How can we immerse ourselves in those cities today?
What are the different social infrastructures, physical infrastructures that can be created in which we can all come together and thrive?
What's really important about looking at this through a world-building lens is that it is designed to look forward and then thread back into the present. The further out you look, the more it changes our view of the present.
We're literally forced to not only reimagine our communities, but to rediscover our neighbors, to rediscover many of the things that are right in front of us.
We're spatializing narrative and allowing the user to tell their own story as they navigate the experience of this virtual cityscape.
What can a megacity grow toward so that it's serving a better purpose? You start looking at individual buildings then, because you can typically shape a building. And can you connect several buildings together?
The buildings might form coalitions and interact with the utility, and the utility will interact with the providers of energy all around. That becomes a transactive energy system, and the buildings can play an active role.
I can design a microgrid that serves that district. Or if we need the microgrid to serve an adjacent district, we layer those together.
We need a water supply system that can meet 15 million people's needs.
Every building in the future should be capturing sunlight and rainwater, and every building should be recycling its own waste.
Ideally, the life cycle of infrastructure is one that is continuous, or perhaps reused in the future without going back and re-emitting all that carbon to do the same thing over again. That's the way we've built over the last century, and we simply cannot do it anymore.
Buildings are not unlike a human body. They have bones and skin. They consume energy and regulate temperature and generate waste. What if architects use genetic tools from synthetic biology to encode the architecture of buildings right into the DNA of organisms?
The facades now become active components. And one active thing that facades can do, they can breathe or they can sweat.
You can infuse biological functionalities into structural building materials.
Almost 100% of all the controls in buildings are going to have some element of AI in them and machine learning. As you walk into the building in the morning, the building will recognize you by your electronic signature. You would have created a profile about your temperature, your ventilation preference, and then some of this microenvironment might follow you.
What would social cohesion look like in the city of 2070? It's reasonable to expect that it would actually be vertical.
So, going vertically also brings its own challenges in terms of safety and security.
You might have 175 drones coming in at 11:45 a.m. delivering lunch. Where do they land? How much space are between them? What are the specifications?
It just has to be designed in a way that people can interact, and making sure that you're encouraging paths of travel that are spontaneous.
We're at just the right point in time to get together and build basically the aerial equivalent of what we did in this country with the national interstate highway system, and no longer be restricted to 2 dimensions.
So how do you get the public involved in civil engineering, in the process of civil engineering?
One of the best ways that we can make sure that all voices are heard and included is to start with the people who are doing the planning and developing and see what their teams look like.
How can you ensure social equity and social justice and get input from the community for the projects that we're working on?
We are very conscious about the demographic, the diversity of the community and the society, and make sure that we don't leave anybody behind.
Creating these multi-use spaces is one way of doing that, of bringing people together. And once they're in the same shared space, there is more opportunity for connection, there's more opportunity for shared experience, there's more opportunity for civil dialogue.
The best solutions on Earth, they come with diversity of thought. What I love most about the Future World Vision Project is that we can think about it together. We can have this dialogue.
Users will encounter one another and have conversations across disciplines that will begin to feed back and bring new information into the system.
We're trying to build a world and trying to build a machine that is creating absolute engagement of the user and of the engineer in their own future.
The Future World Vision is really at the core of what we're trying to do at ASCE in transforming the idea of what a civil engineer can be. And that's how we think that we can advance the profession of civil engineering and attract the best and brightest.
Oh my goodness, this 4th Industrial Revolution, married to the fundamentals of concrete, glass, and steel, is this incredible toolbox for society. It's really on us as civil engineers to pull that all together.
Thank you. Such an inspirational video for civil engineers and how we can shape our future. On behalf of the ASCE Texas section, I'd like to thank Mark Waggoner with Walter P. Moore for his presentation. And thank you all for attending. That concludes this keynote session. Thank you.